the next type of functions that we will see are what are known as exponential functions. Okay. These are very important. The exponential function shows up quite often in circuit analysis, and before we see a circuit situation in which it shows up naturally, I would like to show you how to plot an exponential function, how to think of an exponential function, etc. Okay, so let us begin with a very simple example. Let us look at the function f of x equals 2 power x. Okay. This is a very simple exponential function, and let us try to plot it. Let us see what happens if you try to sketch it. Okay. So, maybe this is x and I start at 0 and 1, 2, 3, 4, etc., and maybe minus 1, minus 2, minus 3, minus 4, etc. Okay. So, the easiest point to evaluate 2 power x is at x equal to 0, and at x equal to 0 you actually get 1. Okay. So, we know that 2 power 0 is going to be equal to 1. So, let us look at 2 power 1, that is going to be 2, we know that is easy, and then 2 power 2 on the other hand is going to be 4, okay, and that is 3, and then that is 4, okay, and so on. It increases quite fast. 2 power 3 is going to be 8. So, the way it increases on the positive side is going to be like this. Okay, it will go up like that, and it will be a smooth function. Okay, so think about why it will be a smooth function. It will increase smoothly like that. There is no jumps or anything. Okay. Now, what happens for x less than 0? Again, it is going to be smooth. 2 power minus 1 is going to be 1 by 2, half. 2 power minus 2 is going to be 1 by 4, which is a quarter, etc. And if you extrapolate and plot like this, it will once again be a smooth function, and it will look like that. Okay, it will go off like this. Okay. That is how 2 power x looks. Okay. So, a few properties that are very easy to see. 2 power x is always greater than or equal to 0. In fact, it is actually greater than 0. It is never equal to 0, right. When does it become equal to 0? Only when x equals minus infinity, and that is not going to happen. So, 2 power x is greater than 0 always. It is positive always. Okay. Another interesting function which you might see is, let us say, maybe I should use a red color for this. You might want to look at let us say g of x, which is 2 power minus x. Okay. How will 2 power minus x look? You can go through the calculation. It is basically going to be a flipped version of this 2 power x, right. Whatever happened in the negative values of x for 2 power x would happen for positive values of x for 2 power minus x. Okay, and it will just be a flipped version, and you can plot it like that. It would go like this way, and then hopefully like that. Okay. So, you see that is g of x, which is 2 power minus x. Okay. So, hopefully you see this point. Whatever value I put here, whether it is 2 power minus x, 2 power x, or 3 power x, or 4 power x, at x equal to 0, it will always pass through 1. Okay. Any a power x will pass through 1 at x equal to 0, right. So, that is something you know, and for if you have 2 power minus x, that is going to decrease like this, decrease very, very fast as x increases positively. On the other hand, if you have 2 power x, it is going to increase very, very fast. Okay. So, in the exponential function, you have to pay attention to a couple of things. One is, okay, so let's look at a general exponential function. If you look at a power x or a power minus x, okay, at x equal to 0, both of them are equal to 0, both equal to 1, I am sorry. At x equal to 0, both of them are equal to 1, and as x increases for positive x, a power x, okay, let's first a power x and a power minus x behave in different fashion. Okay, a power x increases exponentially or very quickly if a is greater than 1, and a power minus x decreases very quickly, falls off to 0 very quickly if a is greater than 1. Okay, so 2 is clearly an example where I took it's greater than 1. So, this is what is going to happen. On the other hand, if a is less than 1, you can also quickly see that the opposite would happen. If a is less than 1, a power x is going to decrease for a for x positive, and a power minus x is going to increase for a positive. Okay, so, you can think about why these things are true, and the basic reason is a power minus x is the same as 1 by a power x, which is the same as 1 by a whole power x. Okay. So, it depends on whether or not a is greater than 1 or less than 1. If a is greater than 1, 1 by a is going to be less than 1, and if a is less than 1, 1 by a is going to be greater than 1, and the same behavior holds true. Okay. So, this is the exponential function, and you might want to sketch it and look at it and how it behaves for various values for a and x. And in typical examples, we might have something slightly more complicated. You might have a power say cx. Okay. Now, there are a few constants here. First of all, a is thrown in, and then c is also thrown in. Now, whether or not, so whatever happens to a or c, if x is 0, a power cx is 0, that we know very easily. So, maybe I should take this example in more detail. This is an important function to get your head around. So, let us look at this function f of x equals a power cx. Okay. Now, f of 0 is going to be 1. For whatever value of a, whatever value of c, it is going to be equal to 1. Now, for x greater than 0, f of x increases under various conditions. For instance, if a is greater than 1 and c is greater than 0. If a is greater than 1 and c is greater than 0, f of x is going to increase. And there are so many other situations. For instance, a could be less than 1 and c could be less than 0. So, if c is negative and a is less than 1, it again starts to increase. So, all these kind of arguments you have to carefully make, and you might want to list conditions under which f of x decreases for what combinations of a and c, and you will get an idea of how exponential functions behave. Okay. In particular, we will be interested in the case of f of x equals e power x. And what is this e? This e is this number which is something like 2.7 something. Okay. You might know the definition for e. E has a very simple series definition. Even if you do not know, just think of e as some constant which is greater than 1, okay, 2.7 whatever. Okay. So, if you have a function e power x, how is that going to behave? I know e is greater than 1. So, at 0 it is going to be 1, and then for positive it is going to decrease, for negative it is going to go like that. Okay, that is how e power x is going to behave. How is e power minus x going to behave? E power minus x is going to behave like that. Okay, this is going to be e power minus x. Okay. So, this e power x is a function that we will obsess over in this course. It will come up again and again in so many different forms. It will take sometimes real arguments, complex arguments, positive arguments, negative arguments, and you should be really comfortable with e power x. Okay. There is a series expansion for it. There are various ways of thinking about it and computing it, but to me the simplest notion is to simply think of e as a constant, 2.7 whatever, and then e power x is a simple exponential function like 2 power x. Instead of 2, you have 2.7 something, this number e. Okay. There is also the logarithm function, which is the inverse of the exponential, and I will let you read it up on your own. I will not describe that in this class, but it is the inverse of this e power x, and think about what that means. Okay. So, this is the exponential function. In particular, we will look at functions of this form, e power minus a t, okay, where a is a constant, and you should be able to sketch this very easily. If a is positive, this is going to start at 0 and decrease as time goes forward. If a is negative, this is going to start at 0 and increase as time goes forward. Okay. So, this kind of function you should be very comfortable with, and the exponential function will play a crucial role again and again in this class. Okay. Why is it that the exponential is important? Why is it that it shows up in several analyses? The basic reason is the derivative of the exponential is itself. Okay. So, if you take the derivative of e power a t or derivative of e power t, we know from basic calculus that this is equal to e power t. Okay. So, this ends up being very crucial in solving differential equations and all that, and that is why this function shows up again and again, and it is an important function to know very, very well. Okay. So, let me see where we are. We started with the constant function, we looked at the step function, and then we looked at sinusoidal functions, then we looked at a combination of the step function and the sinusoidal function, and then we looked at the exponential function. And I want to sign off this little refresher with a discussion of a simple AC circuit which I will try to solve. And when I solve that, you will see some differential equations show up, and this exponential will show up as a solution for those differential equations. And these are important for solving circuits. You might have learnt it before, but it might be good for you to see it real quick in this refresher. Okay. So, here is the simple circuit. I have a DC voltage source V volts, and there is a switch which is thrown at t equal to 0, and there is a resistance R and a capacitance C connected to it in series. Okay, this is a very simple circuit. It is also called an RC circuit because it has an R and a C, a series RC circuit. Okay. So, now you should know a few facts about the components of a circuit. We know a voltage source behaves in a very simple fashion. The voltage across its terminals is always V irrespective of what happens. Now, the resistor behaves a little bit differently. Let us say the current in this circuit is I of t. Okay, I of t is the current that is flowing in this circuit. So, when you throw the switch, some current will start flowing, and you might know from your circuit theory that ultimately it will die down to 0. So, the current is going to change over time, and that function is I of t. Okay. Now, from your loop equation, one can write a very nice equation here. The voltage V, you know, is going to be equal to the voltage drop across the resistance, which we know from Ohm's law is simply I of t times R plus the voltage across the capacitance. Now, the voltage across the capacitance also varies with time, and I am going to call that Vc of t. Okay. So, hopefully you understand why functions of one variable are important when solving circuits, to understand circuits and networks. Clearly, they show up all the time because the voltages and currents in your circuit are functions of time, and when you turn the switch on, when you start exciting your circuit components, the current flowing through them, the voltage across them varies over time, and you should be able to deal with functions of time to be able to solve for the voltages and currents. That is the simple fact of life. So, now there are other equations relating I of t and Vc of t. What is that? That is the current through the capacitance. We know that I of t is C times d Vc of t by dt, the derivative of the voltage. Okay. So, now if you plug that back in, you get V equals R C d Vc of t by dt plus Vc of t. Now, this is an example of a differential equation. With constant coefficients. Okay. So, clearly, to be able to solve for the voltages and currents in this circuit, I should be able to solve this differential equation. In this differential equation, what is unknown? In any equation, there is an unknown which you try to solve. In this differential equation, the unknown is the voltage Vc of t, which, as I told you, is a function of t. So, you have one equation which tells you, which gives you, okay, we have one equation which involves an unknown Vc of t, which is a function of t, and you have to solve for it. So, now one critical thing to remember is that this equation holds for t greater than or equal to 0. Right. So, of course, if t is equal to 0, t less than 0, then there is no current, I of t is 0, there is no voltage drop across the capacitance, nothing happens. So, that is always understood here, only for t greater than or equal to 0, this is true. Okay. So, now one needs to have some general techniques for being able to solve these kind of equations. and I am not going to go into great details here, but you will see these techniques as part of this course. You might have learnt it before in your circuits course, but if you have not, in this course you will see it in a slightly more advanced way. But let us try and write down the answer. It is not very hard to write down the answer. The answer, if you can guess that, will involve the exponential function, and it will be of this form: v times 1 minus e power minus t divided by RC. Okay. So, now I know this answer from past experience, but even if you do not know, you might be able to solve it. But particularly if you know that this is the answer, one can check whether this answer is valid or not. Okay. So, it is not very hard. How do you check if it is valid or not? You plug in Vc of t into this equation, and you will see this equation will be satisfied. Okay. Vc of t will come here, you have the derivative here. In fact, if you take the derivative, you will see the RC will cancel and you will get a t by RC out there, and then there will be a V term coming in, and it will exactly cancel with the other guy on this side, and you will get V. Okay. This is a simple exercise which I will urge you to try, that this solves this equation, and of course, this is true for t greater than or equal to 0. Okay. So, the main reason why I showed you the solution is to tell you that the exponential function is very important to understand circuit analysis. It shows up naturally as the solution of even the simplest of circuits out here. Okay. A simple RC circuit, if you throw the switch at t equal to 0, the exponential function is involved. So, now if you want to plot this, it is interesting to plot this guy. Okay. Now, remember, all the action is for t greater than or equal to 0, for t less than 0 you just have 0. Okay. And what happens at t equal to 0? At t equal to 0, we know that the exponential function takes the value 1, and 1 minus 1 is going to be 0. So, the voltage across the capacitance is 0. So, now you might know this has to be true, because the voltage across the capacitance cannot jump. There cannot be a discontinuity in the voltage across the capacitance. The reason is the current is actually the derivative of the voltage, and if there is a discontinuity, things are going to blow up in the circuit. So, that is not very nice in our model. So, that will not happen too much. So, it is nice that we see that this happens. And the other thing that is going to happen is you have here 1 minus e power minus t over RC. This is a slightly more complicated plot than what we saw before. We simply saw e power minus t by RC. How does e power minus t by RC look? This alone would look like this. It is going to start at 1, okay, and it is going to start decaying for positive t. The reason is e power minus t by RC, this 1 by RC is actually positive, there is nothing negative there. So, you have a minus overall. So, the coefficient becomes negative. So, as t increases, this is actually going to fall. Okay. So, now I know this guy is just this plot, right, this alone is this plot. Okay. Now, that is not the Vc of t, it is actually 1 minus this and then multiplied by V. What is going to be 1 minus this? 1 minus this will give you a picture which looks like this, right. It will look like this. Okay. This is 1 minus e power minus t by RC, and then I am going to multiply it by V. So, I get an equation like that, maybe, I do not know, I am just showing it here. Okay. So, it will never exceed V, it will never exceed V, and that is how it will look. Okay. So, it became a little messy. So, maybe I should erase this a little bit and show you how it looks. Okay. So, that is the plot, and you see that this guy is actually Vc of t. Okay. It reaches V as t becomes very, very large, and that you know happens to the capacitor. Okay. So, this is an example of a slightly more complicated function. It involves the exponential, but then there were other manipulations. You had to figure out 1 minus exponential and then multiplied by V, etc. Okay. So, this level of comfort in dealing with functions of one variable is quite important. There will be some examples of this as you go along in the lectures, but I will urge you to refresh yourself with these functions, how to plot them, how to think of them, etc. Okay. So, in the prerequisites part of the course, we are pointing you to several websites and several additional material which discuss information like this in great detail: functions of one variable, what are derivatives, what is meant by continuity of a function, what is a discontinuous function, what is a jump discontinuity, what is an exponential function, what are trigonometric functions, how to define them, how to think of them, how to sketch them, etc. All of this are provided in additional material which we will point you to as in the course pages. I will urge you very strongly to go through those pages, read them at your own pace, make sure you get familiar with these functions, because the rest of the course involves these functions very heavily, and if you are not used to these things, you will be shortchanged and you may not be able to understand a lot of things that are happening. So, I will encourage you to go through the preliminary material very closely. Okay. So, that is the circuit concept, and hopefully you see why functions of single variable are very crucial for being able to solve circuits. If you do not know them very well, it is very hard to solve circuits. Okay. So, for instance, in this problem, in this very same RC circuit, if I change this V, if I replace with the AC source, what happens? Okay. That is an interesting question, and it is not very easy to solve that the way I did. Okay. You might be able to write down a differential equation which will be actually very similar to this. It will not change very much compared to this, but solving that differential equation is going to be a bit more challenging. You need to know some additional tools, and after solving that differential equation, being able to sketch that differential equation is also going to be a little bit more challenging. And in this course, you will see generic techniques which help you solve such problems. Once you master the networks and systems course, when someone gives you a problem like this, you will be able to quickly get to the answer even without doing complicated calculations. For instance, I know because I have studied this course before, that if you replace this DC source with an AC source, right, initially there will be some variations, but eventually after a while the steady state solution, so to speak, is actually sinusoidal voltages and currents in the circuit, and in fact it is possible to even compute that. You might be able to quickly figure out what the transient or initial behavior will be as well. All these things are very important in circuits, and you will get tools, generic powerful tools which will solve these kind of problems as part of this course.